So welcome everybody to this seminar today. Today we have Ruben Verresen from the University of Chicago. Ruben started his PhD, did his PhD on the supervision of Frank Pohlmann in Munich and Roderick Mössner in Dresden, studying topological matter and tensor networks. And he spent also 6 months as a graduate fellow at in Santa Barbara. Then he moved to the US as a HQI postdoctoral fellow in the group of Ashwin Vishwanath in Harvard. So he worked in there on the opportunities arising from innovations in quantum technology. And after spending a couple of years there as a postdoc, like in MIT and Harvard jointly, he's now starting his own group at the University of Chicago. So congratulations for that. And now he will talk about quantum phases of matter and the Toric code.
Thank you very much, Matteo. Was for the nice introduction and for the invitation. So hi everyone, it's great to be here. I'm excited to tell you about some fun stuff. So today is not related to my research just. It's kind of a beautiful, important topic in many-body physics. But also some of the topics I'll be touching on will be some of the stuff are old, quote unquote, from the 90s and early 2000s. Other stuff are touching onto the kind of ongoing research as well. So this kind of topic I'll be discussing is quite topical, but it's also just really, I think, conceptually interesting. And so yeah, so as Matteo kind of introduced, I'm Ruben Verresen. I'm a condensed matter theorist, roughly speaking, and indeed, so in the fall I'll be starting at U Chicago. So in my research, I use both lattice-based methods and field theory-based methods. But actually today I'll be talking, I'll be talking purely on the lattice. And I thought maybe I can briefly justify that because I guess it is supposed to be a course on field theory methods, condensed matter physics. But well, there's a variety of reasons why let's discuss the lattice today. And well, okay, it is just a cool topic and it's beautiful, and maybe the reason we're all interested in many-body physics, including field theory, is we're interested in interesting things, and it'll hopefully you'll be convinced it's quite interesting stuff. But also, in these kind of topics, sometimes we want to understand very strongly interacting systems. And field theory methods, can sometimes deal with strong interacting systems, but it's by no means easy. And then it can be really helpful to side by side have a lattice model. So it can be very useful to sometimes have solvable lattice models. And then it's not excluding the field theory approach. It can be very complementary. And in fact, if you have some tractable lattice model, can often even inform what the structure you're looking for on the field theory side of things. So it's very complementary, and it can sometimes even be necessary to make sure you don't miss things, because sometimes the field theory, you might be in a scenario where from a field theory approach might look trivial. You might be in a scenario where, if you use some usual reasoning from field theory side, you might think there's nothing to say. The field theory is empty, so to speak. There's no low energy, massless degrees of freedom within, with which you use to kind of write a field theory, but it can be very deceptive. And the lattice, because it's kind of all-inclusive, the lattice has all the information, so to speak. It can maybe more easily point out certain degrees of freedom one might have easily overlooked in the field theory. And the point is, it's a might. So the field, once one understands the lattice model correctly, one can be informed what is a correct field theory, and then one finds indeed the field theory is not trivial, right? But it can just be it can be a bit deceptive sometimes. And to be clear, the things that are, were missed out are actually very interesting. So it'd be unfortunate if the field theory approach had misled one, right? So it can be, again, very complementary. And also the topic that I'll be discussing today has some relation to other guest lectures. So if I understand correctly, you already had a guest lecture by Steve Simon. So if I understand correctly, he talked about fraction quantum Hall effect and the related topic perhaps of topological states of matter, these kind of states of matter that appear there, with whose emergent quasi-particles are very interesting. So maybe for example, topic of anyons has been mentioned. And that's an example of kind of systems where the field theory might look very innocent on first sight, but in that case, experiment forced upon us that there's actually a very rich arena to explore. And today I'll be talking about, in some sense, similar universal phenomena, but in a much simpler setting, in a sense of a lattice model you can completely solve and you can understand all the properties. And it's not literally the same as the phenomena that happens in fraction quantum Hall, but it's a similar kind of, I don't know if Steve mentioned topological phase of matter, but it'll be an example of a topological phase of matter. So it's very complementary in that perspective, I think. And then also, I think Alexander Altland has yet to give a guest lecture, but if I understand correctly, he'll be talking about lattice gauge theory, at least is what I heard. And if so, then what I'll be discussing today also has direct links. It doesn't overlap, hopefully, but some of the phase of matter I'll be discussing and the models, they have tight connections to lattice gauge theory as well. So yeah, I thought it could maybe be a useful topic to discuss in the context of the other things. Oh yeah, and maybe a last point I do want to mention is, I guess, right, if one zooms out, usually one reason to prefer field theory, right, if one can solve it, is it maybe makes more easily apparent what are the universal parts, right? Because the problem with a lattice model is it is what it is, and at face value, because it is everything, right? The lattice model includes all information. It might not be clear which properties are some coincidental. Okay, that happens to be true for this particular model, but it's maybe not generic. If I perturb away, it might have some fine-tuned features. And field theory, because it's written in more minimal kind of variables, it usually might make more apparent what is universal. But the nice thing is, at least the type of lattice models I'll be discussing, it does allow you to make universal arguments. So you can make, in some cases, you can make universal arguments on the lattice. Even in absence of a field theory approach. And again, that can be very useful, for example, in these strong interacting systems, where the field theory can be very challenging. If one has some handle on the lattice, it can actually, sometimes the lattice in that sense can help understanding universal aspects. Yeah, also I should mention, feel free to interrupt at any point or questions. From my perspective, today I have no particular set of topics I have to discuss. I have plenty of things I'm happy to discuss. But I guess the main point is just to, discuss some interesting concepts. So yeah, the more discussion, the better, as far as I'm concerned. Okay. So, and as the title suggests, I'll be talking about a particular type of nice lattice models called the Toric code. But rather than jumping straight in, I think, maybe to also build some appreciation for it and to give a sense of the broader landscape, I want to first zoom out a bit and introduce this more general notion of quantum phase of matter, of which the Toric code is a nice example. And apologies if some of this overlaps with the things we've seen already. I mean, I had a quick look at the lecture notes that were available online, so I don't think it's going to be literally coinciding with one of your lectures, but okay, some of the concepts will naturally relate to what you've seen before, perhaps. So let me start with quantum phases of matter. And so, when you think of many-body interacting systems, one scenario that often appears is, of course, finite temperature, right? And finite temperature transitions, Gibbs ensembles, etc. But the nice thing about quantum physics is you don't really need finite temperature to have interesting many-body systems. In fact, sometimes it helps not to have finite temperatures. So there will be rich physics even at 0 temperatures, where the idea is that, even though there's no thermal fluctuations by definition, quantum physics, one way of thinking about it, you have these non-commuting variables, so that also introduces fluctuations, right? Sometimes called quantum fluctuations. And those quantum fluctuations can somehow replace the role of thermal fluctuations in classical stat mech. And so quantum fluctuations in a quantum context can stabilize a very interesting phase of matter. And in that scenario, we don't think of Gibbs ensembles as such. We do still start from, you specify the interactions of the system, right, as usual. And the rules we usually play by is that we are interested in local interactions. So oftentimes kind of the defining feature of the problem is that you look at a local Hamiltonian describing a quantum system. So I know one Hamiltonian you've been introduced to already, and a quantum Hamiltonian, I should say, is something like the Hubbard model, right? So there you might have some charges. Here I'm writing this kind of second quantized notation. So here's some kind of maybe some fermions that live on a lattice that are hopping around. And then maybe there's some Hubbard interaction, I think you've seen. So where, you know, you can think of like little electrons localized on orbitals, and if they're on the same site, the different spins might interact. So that's something like this. And then maybe you have a chemical potential and maybe have other terms. You know, that's kind of a Hamiltonian you can imagine defining. And then we might be interested in the ground state properties of such a Hamiltonian, right? The kind of the zero temperature properties, and kind of very rich, interesting emergent physics. Or, you know, another typical type of Hamiltonian people study is something called a spin Hamiltonian. So, for example, let me first write it down and then explain. So, one way of writing it is as some kind of spin vector. But then if I specify to a spin a half, it might look like you're just wrote it in maybe in one case. So for example, might looks like something like this. And I'll introduce this notation in a moment. These are supposed to be components of some spin. So I think you see, at least it was mentioned before that, for example, if you start with this top Hamiltonian, which is arguably kind of a physical Hamiltonian that describes a lot of actual systems, if you're in the large U regime, if interactions are very strong, you go into something called a Mott limit. We don't have to worry too much about what precisely that means. But the point is, if you have, say, electrons with some spin degree of freedom, and I can point up or down and electrons are hopping, you can imagine that if interactions are of a certain type, maybe their motion degree of freedom is quenched. Maybe they don't like hopping around. But even if they're not allowed to hop around by strong interactions, their spin degree of freedom can still, you know, be in a certain configuration. So it's still a quantum degree of freedom you can take into account. And so in the scenario where you can entirely forget about the motion, right? The electrons are no longer hopping around, but they're stuck. You get a model that only describes their spin configuration. So you get something, you know, something like this, which is also called a spin Hamiltonian or a spin model, because that's the only degree of freedom you take into account. And it's also sometimes called a bosonic model. And of course, fermions, as the name suggests, are fermionic degrees of freedom. But the point is, once you don't allow them to move anymore, and the only degree of freedom is their spin, in some sense, you know, the fermionic statistics, the fermionic properties go out the window, and you can really think of as a system where observables commute. Because if I have a spin on one side and a spin on the other side, there's no sense in which those are anti-commuting observables, because they don't, you know, hop around different sides and get exchanged. And it can turn out to be very useful to think about these pure spin systems. They're actually very interesting. And even though in some sense it's a reduction of the problem, like we've ignored fermions, there's two advantages. It's on the one hand, you're automatically going to be in a strongly interacting regime, because the very reason these effective systems arise is because of strong interactions that prevent hopping around. So it's probably an interesting place to look if you're interested in strongly interacting phenomena. But also at the same time, it reduces the complexity of variables, right? You don't have to worry about the whole motional degree of freedom. And as I'll hopefully convey in today's lecture, it can, you know, allow it to write down some solvable models with very interesting phase of matter, and to study full fermionic versions where the charges are really hopping around would be considerably harder. So that in some sense, it's both, you know, more difficult because it's strongly interacting, but also easier because it's a reduced problem. And the scenario we're kind of looking at then in these kind of systems, for example, you might have little, you know, spin a halves living on, say, vertices of a lattice. Which lattice, etc., depends entirely on, you know, what problem you'd like to study. And when I say spin a half, basically, you know, just think of these the spin of an electron, right? It can either point up or down, so it's a two-level system, or it's also sometimes, you know, called a qubit, right? So it's like a two-level degree of freedom. So another way of thinking about it is we're going to be looking at lattice models where on each site of the lattice model, we have a qubit, a two-level degree of freedom. And then a very useful kind of way of expressing operators or observables in that kind of two-level system is by using poly operators, which I already hinted at here. So I don't know if you've seen that. So let me briefly review those. So, I mean, very briefly, they essentially are defined by the following algebra. So you have three, as you saw here, sigma x, sigma y, sigma z. The intuitive pictures have in mind that they're roughly kind of measuring whether a spin is pointing along the z direction or the x direction or the y direction in internal spin space, right? Like the spin has some direction. But it corresponds very concretely. So if we're on the same site, say site I have a sigma x operator, sigma y, and the point is they don't commute. Right? Classically, if I have a spin pointing in the x or y or z direction, they're commuting observables, as anything is in classical physics. But in a quantum world, things don't commute. If I measure whether a spin is pointing along the z direction, I might influence its behavior along the x direction. And that's expressed in this commutator relation. Okay. And this is exactly the kind of thing one can derive if one starts with actual electrons with spins, and one freezes their motional degree of freedom out, and you get localized spins. You can derive that these are the effective observables describing the remaining spin. But as is often the case, one can write down concrete matrix expressions of these kind of operators. So concretely, on a single qubit, these operators, observables, can just be expressed as follows. Here's a particularly useful matrix representation. So 2 by 2 matrix because it acts on a 2-level qubit. And one can check that this satisfies this commutation relations. And there's some other useful properties. In particular, note, for example, that sigma squared is 1, and same with sigma z squared. So these they're called polymatrices. Oops. They have very nice algebraic properties that makes it quite pleasant to work with them. So, for example, each of them squares to 1, and you can also see, that's what this commutation relation says essentially, or you can show that they anti-commute if they're not the same. So maybe clear to see with poly x and poly z, they anti-commute. So there's some quantum physics there. And then finally, this third relation tells you that the third polymatrix is essentially obtained as a product of the other two. Okay, so it's a very nice set of algebraic relations. And oftentimes when we're studying quantum magnets, or I should say spin models are also sometimes called quantum magnets, just for the fact that magnets involve spin degrees of freedom. We're talking about spins. So I'll use these words interchangeably, quantum magnets, spin models. These polymatrices are really kind of the essential workhorse of what we use to define and manipulate these models. So I don't know if this might not have been covered in this course. Actually, I don't know if polymatrices have been discussed, but okay. Yeah. Let me know if there's any extra questions about it. And then notation-wise, because it's a bit annoying to have to write sigma x, sigma y, sigma z, sometimes I'll just use x, y, and z. Okay, but just shorthands for these polymatrices. Okay, when you see x, y, z, capital letters, I'm always referring to these kind of polymatrices. Okay, and then again, that's for a single qubit, but now if you have a lattice model, right, you might have, say, polymatrix on side 5 and polymatrix on side 4, and note, because they're bosonic, if you have, say, polymatrix on different sites, they commute. In that sense, that's why people use the word bosonic sometimes for these models, because observables on different sites always commute. Okay, so and then maybe I should mention the Hilbert space, right? Because if you have a Hamiltonian, it's supposed to be defined on some vector space, and the Hilbert space is basically so-called tensor product of a single qubit, where n here is the number of spins or number of qubits, and H qubit is just a 2-level system. So in other words, the dimension of the total Hilbert space will be 2 to the n. Okay, so it's of course a very big Hilbert space as we expect in quantum physics. but I'll be talking about these kind of Hilbert spaces in today's lecture. So we'll be ignoring fermions, but again, if you like the physical picture, just think of each spin as an actual fermion who just cannot hop around, and you only have the spin. Okay, so that will be the ingredient of how to define a physical system, right? It doesn't have to be realistic. We don't care if, depends a bit on some people are only interested in physical materials, but I'll take the broader point of view. We're just interested in knowing what can happen when you have interacting quantum systems. Can we learn something cool? And then your Hamiltonian essentially defines your system. And then in the topic of quantum phase of matter, we're interested in, as you might guess, the phase of matter that the ground state is in, okay? So in particular, if you have a Hamiltonian, it tends to have a bunch of parameters, alpha, beta, gamma, beta. And this could be, as for example, as shown here, it could be, say, the Hubbard interaction, it could be a chemical potential, or maybe, for example, this would be an anisotropy, where not all spin interactions have the same strength. So for example, chemical potential, Hubbard interaction, or anisotropy, etc. So we have this Hamiltonian with a bunch of parameters. And then we're interested at zero temperature in the ground state, right? So that'll be a pure state, right? There's no mixed states at zero temperature. There's no Gibbs ensembles. So there'll be the actual ground state. And then, of course, that ground state will, of course, depend on the same set of parameters, right? And then that is, of course, you can think of it as a vector of your total Hilbert space. So my sound was just... Oh, I just had to change my audio setting. Can someone say something just to make sure I still can hear you?
Hello. Yeah, can you hear me?
Thank you. Thank you. I just had to switch off my speakers. Okay. Okay, good. And then as soon as you have this parameterized wave function, it opens up the question of what is a landscape. So in particular, one can then consider this. Once you have this parameterized wave function, you can ask about the ground state phase diagram. So schematically, draws a big blob. And the point is, each point is some pure state, is some ground state, right? And then it might be parameterized by, alpha, beta, gamma, whatever, whatever is parameterizing our wave function. So we have this whole landscape of states. And then we want to know what are the physical properties of these states, which states are in some sense in the same phase and which are in different phases, right? So we've all encountered the notion of phase of matter, right? And water, like liquid water and ice, are different phases. Similarly, you could ask about quantum states, and then you get this kind of phase diagram emerging, right? So for example, this will be phase 1, phase 2, etc. And of course, I haven't yet precisely defined what we mean, but the idea will be, anything in the same box will have the same physical properties. That's what we want. That's the whole point of a phase of matter. You want to select out universal, long distance, robust degrees of properties, as opposed to any coincidental stuff that could have easily changed. So anything in the same region is the same physical properties in the same phase. And then obviously the point is, things in different sites have different physical properties, which then necessitates a phase transition. So in particular, these red lines denote so-called quantum phase transitions. So again, we're not tuning temperature, we're just tuning some parameter in our Hamiltonian, but it could be that, anywhere, say in these extended regions, the wave function transforms very mildly as you tune the parameters, nothing singular happens. It might be that at certain points in parameter space, suddenly your correlation length, your wave function dramatically changes. For example, correlation length might diverge. You might have certain singularities in the wave function, and that we call a quantum phase transition. In particular, in practice, it means that certain observables change in a non-analytic way, right? There might be cusps or critical exponents that appear. And they appear between different phases of matter, right? And of course, these phase transitions themselves might be very interesting, right? So in this kind of quantum phase of matter, you're interested both in the phase of matter and also the transitions, because they can really be interesting. For example, they can often be described by some emergent scale invariant theory, maybe described by something called conformal field theory. And this is not something I'll discuss today, but the point is it's a very interesting type of field theory with emergent scale invariance. And the nice thing about these lattice models is that usually we put in very little by hand. For example, on lattice models, you don't impose Lorentz symmetry as a natural symmetry, because once you have a lattice, space and time are not related by a certain symmetry. Right? Time evolution is continuous, but space is discretized on the lattice. But remarkably, especially when you tune these lattice models to a critical point, you can show that low energies, Lorentz symmetry might emerge as an emergent property. So emergent Lorentz invariance, which is actually already very interesting. And once you learn how much can emerge for free, it also really begs the question, right? Like we usually think of Lorentz symmetry, relativity, right? They're kind of very related as being fundamental properties of standard model. But once you learn that these properties can in principle emerge from a model that doesn't have it, it really begs the question, what do we even know is fundamental, right? Once you know something can come for free, it's not as obvious that we really need to presume it at a fundamental scale. So that's an extra, at least personally, that's an extra reason I'm interested in kind of many-body physics, is the kind of exploration of what you can get for free from specifying seemingly very innocent set of degrees of freedom. To drive that point home even a bit more, right in the beginning, I started off saying we're going to ignore fermions in some sense. We're going to pin their motional degree of freedom. So we're going to have only bosonic systems, like little spins, that could exist in the universe without fermions. But again, we'll touch on this. If those degrees of freedom are strongly enough interacting, it can be that low energies, fermions, emerge as effective degrees of freedom. So even if you start with a bosonic field theory, if there is interacting enough at low energy, you can get emergent fermions or even more exotic particles. So again, apparently fermions don't need to be fundamental. They could emerge for more simple degrees of freedom. Anyway, so that's kind of the setup that we're imagining. Where you specify Hamiltonian, and then you want to explore the phase diagrams of its ground states, and learn some interesting things, and maybe to maybe make clear what kind of questions are typically asked. There's a whole bunch. Let me just maybe highlight a few. So, okay, a natural one is, which phase of matter arise in a particular setup? And of course, that answer will depend on, how you set up the problem, right? As I emphasized here, much of the problem causes, is also in terms of specifying your Hilbert space, right? For example, today's lecture, I'll be talking about spin Hilbert spaces, where I put spins on a particular lattice, but you can choose your dimensionality, you can use your type, your type of spin, or you can go back to the Hubbard model, right? You can set your stage, then ask within that realm, what are the different types of phase of matter you can get distinguished by critical points, right? And then relatedly, what are universal properties of them? But also let me highlight maybe kind of goes hand in hand, but which types of critical points can emerge, or in other words, what I was calling quantum phase transitions. I will use those terms interchangeably. Because I just try to emphasize they can be very interesting in themselves, right? So if you're interested in conformal field theory, etc., sometimes you can discover some new ones, right, by just exploring a lattice model, tuning to a critical point, and studying its emergent properties. Also, a fun question is, which is not actually that obvious, kind of relatedly, like how many, let me call this quantum phase transition in short, QPT. How many quantum phase transitions between two phases of matter, right? For example, if I specify we're interested in this phase and in this phase, and I can go this path or this path or this path, will they all, at the critical point, will they all be described by the same field theory, right? And maybe the minimal guess is yes, because somehow you might expect that there's this physically motivated, it's minimal field theory that's consistent with like going from one phase to the other, but doesn't have to be the case. People are quite recently exploring examples of something called multiversality, where exactly the opposite happens. You can have different types of field theories describing critical points, even though you don't change the phase of matter on both sides. And in addition to knowing how many types there are, also kind of asking like how to detect these things. Right? You might, in principle, know that there's a certain number of phases of matter, but how do you know whether you're in box 1 or box 1 or 2 or 3? Is there some observable you can detect, an order parameter? And as we'll explore, it's not always obvious. Actually, it can be very subtle to know which phase of matter you're in. And the usual rule of thumb is the harder to figure out which phase you're in, maybe the more interesting the phase of matter is, because it tells you it's usually the phase of matter that are easy to detect are the ones that admit some kind of simple classical description, because that's the cases where we can easily think of some kind of simple order parameter. So the harder it is to figure out how to detect something, usually the more quantum-y it is. We'll see some examples. And also, depending on how familiar one is with these kind of questions, you might wonder, right? Like I seem to have done this ridiculous reduction where you start with a many-body Hamiltonian on this immense Hilbert space, right? It has a 2 to the n, energy eigenstates, right, to define the Hamiltonian. And suddenly I'm just only going to look at the ground state. It seems a bit like, what about all the other stuff that makes the Hamiltonian interesting? And you might ask, like, is there a relation between the ground state and the excited states? And a priori, I think it seems a bit, unrelated, perhaps. How can the ground state tell you about what the excited state properties do? Because naively, maybe you could tune those separately. But it turns out there are deep connections, and I'll try to highlight how knowing the ground state informs what are the excited properties of the Hamiltonian, and has to do with the emergence of certain types of quasi-particles, etc. So that's maybe one reason why it's actually not such a massive reduction. It's about, it doesn't just tell you about the ground state, it tells you about the whole kind of low energy part of the Hamiltonian. And of course, other, there's a bunch of other general questions. For example, you might ask about finite temperature stability, and maybe ultimately might be most interested in things which could have survived if you tune up a little bit of temperature, etc. And there's many more questions to explore. But I just want to give you a sense of what are the things people have in the back of their minds when they're exploring these kind of systems. Let's see. Right. So that kind of sets the stage a bit. Let me just briefly stop and see if there's questions at this moment. That's good. Okay, so let me now introduce something like a key notion that really organizes one's thinking about these kind of questions and setups. So a very useful notion, and in some sense a restriction, I'll make clear. For studying these kind of questions, actually, for both defining more precisely, because I haven't defined for you quite precisely yet what I really mean by phase of matter, and for kind of characterizing them, characterizing phase of matter. Is a notion usually called the, let me put it in red because it's very important, the energy gap. So what this will refer to is basically how much energy it takes to excite above the ground state, right? So in particular, if you have your Hamiltonian H and you diagonalize, right, we know in principle you get a whole energy spectrum, right? And say here's the ground state. And then we can, here's the first excited state. Then you can ask, what is the energy separating the ground state and the first excited state? Let's call that delta, which is, say, called the gap, the energy gap between ground state and first excited state. If this gap remains non-zero. So for finite system, generically it will be non-zero because things are, if things are zero, it's usually for a reason. It's more generic to be, to have separation between energy scales. But if this gap remains non-zero, when the system size, and I'll usually use L for kind of a linear system size, for example, square lattice, L by L. When the system size L goes to infinity and the gap remains non-zero, we say the system is gapped. As a shorthand for that statement. Right? So physically, it means no matter, like if the system is very, very large, no matter how large it is, it will take some finite energy cost to go from the ground state to the first excited state. Let's see, there's a question in the chat. Okay, so someone in the chat asks, is the tuning between phase of matter related to adiabatic transformation? Right, so that's a good question. So let me go back up here. So indeed, so if you're sticking within the same phase, so say here's one, wave function, here's the other wave function. Okay, so, and there's some whole parameterized path. Let's say this is, let me give this some parameter. There's a parameterized, so we know by construction there's a path of local Hamiltonians parameterized by lambda, and if lambda is 0, you're over here. If lambda is 1, you're over here. And if they're in some sense in the same phase, as I'll introduce in a moment, you can indeed, what it means, you can adiabatically transform one ground state into the other. So for example, if you might start with this ground state, and it's Hamiltonian, of which is the ground state, if you slowly in time tune the parameter lambda towards, towards here, if you do it slowly enough, you can show that the ground state of the initial Hamiltonian adiabatically transforms in the ground state of the final Hamiltonian. So that's another reason that we might be interested in the phase of matter, is because once you have one, you can kind of create all the other ones by smoothly changing a Hamiltonian. And that's not a given because it typically breaks down when you tune across a transition. Because no matter how slow you go across a transition, just to make this more precise with time and length scales involved, it's no longer easy to kind of smoothly transform your ground state. Yeah, so there's indeed that connection. Thanks for the question. Okay, let's see. So, and I should mention, when I say the system is gapped, oftentimes we have a slightly relaxed version of this as well. So note, we also allow for a finite, typically finite. I mean, it's pretty hard to find systems that have infinite degeneracy. For a finite degeneracy, so in particular, what I mean, right? So you might have, if you diagonalize a Hamiltonian, you might find like several levels, right, at the ground state energy, and then you have a first excited state. So, this might have several grounds. The ground state does not need to be unique. And the number we call the degeneracy of the ground state. But as long as that list is finite, the main point is then, after ignoring a finite number of states, is there then a finite energy gap to the first excited state? And then again, the same definition applies. If that gap remains finite, we still say the system is gapped. Okay, so it's up to some finite degeneracy. And one reason, maybe connecting to what I just said just now, is that this gap allows you, for example, to prove what I was mentioning about this adiabatic deformation. So to go back up here, this claim I made about being able to smoothly deform the ground state of here into the ground state here, that actually is, really true when the Hamiltonian is gapped. You can use that energy gap to bound the speed at which you can tune the parameters to smoothly deform lambda 0 into lambda 1. Okay. So starting the page. So we'll be looking at so-called gapped Hamiltonians. That's what we're interested in. And physically, what that means is there's the low-energy theory has no massless excitations. Okay, nothing low energy to excite, and that also has a lot of implications in the ground state actually. So the ground state, you can prove, has exponentially decaying correlations. For example, if you calculate any correlation function, something like this, and if you calculate the connected correlation function, so we subtract some expectation value, you can show this decays exponentially quickly with some distance psi. And I should mention, this is not a trivial fact. It's simpler to argue if you have some kind of Lorentz invariant field theory, because you can kind of argue it by doing some space-time rotation arguments. But again, on lattice, we're not given Lorentz symmetry. So actually proven, I would say, relatively recently, and if you think of the history of condensed matter. So it's proven by Hastings, at least as far as I'm aware. It's first proven Hastings and Coma in 2005. So here, let me give you the archive link for those interested in these kind of things. Okay, now it might seem like a massive restriction, right? We don't allow any massive excitation, because if you study field theory, we often, right, are in a situation where you have some massive excitations, at least as a starting point, right, before you might gap them out with some Higgs mechanism or whatever. So this is the point I was trying to make at the beginning. These are scenarios where the field theory might look trivial, right? If I'm telling you there's no low energy massive degree of freedom, it almost sounds like I'm telling you the field theory is quote unquote empty. There's just nothing to write down. There's no degree of freedom. And then, at that face value, you might then move on because, okay, what else is there to say, right? But it's a strong might. It's actually not true. And kind of related question, right? You might wonder, is there more than one such phase? Like how many gapped phases are there? Because, if something is supposed to be featureless, it's hard to have more than one type of featurelessness, right? Like if two things are distinct, they must have some feature that distinguishes them. So there must be something to be said, some kind of field theory. And so the landscape we'll be exploring is, again, kind of similar to what I was sketching before, but now I'll be more restrictive. Before, I was being a bit imprecise. Oh, sorry, what was it? Here, I wasn't really telling you what were the phases of matter. And, for those of you it might have been gapless phase of matter. Like if you've seen Fermi liquids, one of the bubbles might have been a Fermi liquid, other something else, or some kind of QCD phase diagram, etc., which has some gapless phases and photons and whatever. But now it'll be much more restrictive. Each bubble now will be representing, this will be, say, a gapped phase number 1, say, then number 2, etc. So each bubble is ground state landscape of a gapped Hamiltonian. And then in particular, these lines here is when the Hamiltonian has a gap closing. When you can no longer retain this property as a finite energy gap. So now I'm in a position that can be a bit more precise, right? Because how do we want to define phase of matter, like quantum phase of matter? And a typical working definition, even to this day, right, if you would read it like a research article on quantum phase of matter, a large subset of community studies, for example, gapped phases. So we say a gapped Hamiltonian, so let me call it H0, and a gapped Hamiltonian H1 are in the same phase. It's defined by an equivalence relation, the same phase of matter, if and only if, so it's a defining property, if and only if there exists some path of Hamiltonian, some continuously parametrized path, so some continuous parameter that basically which is gapped and connects them. Right, so in particular, when lambda is 0, it's our initial Hamiltonian. And when lambda is 1, it's defined to be our other Hamiltonian. Right, so the picture you can have, it's in the landscape of Hamiltonians in the ground states, it is some continuous path connecting them. And if you can smoothly deform one Hamiltonian into the other while keeping this energy gap non-zero, we say they're in the same phase. And one reason is what I was saying before. If you can connect them by gap path, you can also adiabatically transform one ground state into the other by doing it very slowly, and that should probably convince you that they really kind of have the same properties, because all the universal properties don't really change when you smoothly change this Hamiltonian. And then naturally, there's an if and only if. That also means if two Hamiltonians cannot possibly be connected by such a path, that means we declare them to be in different phases, right? So that happens, for example, if you have Hamiltonian here and here, they simply cannot be connected. For example, this particular path would go through a gap closing in a quantum phase transition. Okay, so the gap closing in particular, right? So just to make clear, so the energy spectrum will kind of collapse here. There's no more energy gap, and it looks a bit horrendous, but often, for example, if we have extra quantum numbers, so for example, if momentum is a good conserved quantum number, right? So we can talk about charges of translation symmetry, so to speak. If momentum is preserved, we can use that to label energy eigenstates. So we can use an extra axis to give some structure. And then oftentimes what happens is that the energy comes down at some momentum, K0. And you kind of see here that there's some kind of immersion field here, or some gapless mode, where energy here is proportional to the change on momentum from the initial gapless point. Okay, so this is now the landscape we want to explore, right? And again, at this point, you might be skeptical that it's something interesting to explore, because again, right, it looks like the field is going to be boring at first sight. But the point is, there turns out to be different phases of matter, and they can have some very interesting properties. And in particular, it turns out gapped phases of matter only come in two types of flavors. Oops. Okay. Come in two types. One type has a classical analog, like we might be familiar from classical physics, but the other one is intrinsically quantum. Okay, so let me start with the more conventional one. The first one is essentially spontaneous symmetry breaking of a discrete symmetry. Spontaneous symmetry breaking, or SSB in short. And the second type, it's sometimes called topological order. Okay, there's a second type that is the kind of correct description for some of the phases that Steve Simon was mentioning. So these he was talking about fractional quantum Hall effect. These are actually gapped phases of matter that he was discussing, but they're definitely not spontaneous symmetry breaking. So they must be in the second class, and indeed they're example of topological order. And one kind of useful practical way of distinguishing them, as I'll try to emphasize as well, is that the first type, the one that has we know from kind of classical physics, can be detected by a local order parameter. So if you have such a state, you can kind of look locally and figure out what you have. But the point is, the second one has no local order parameter. You have to look at much more subtle and intricate things to figure out that you have it. That both makes it harder to detect, as you obviously, but it also tends to endow these states with more stability, because somehow there's a trade-off. The easier it is to detect something, the easier it is to destroy it, because the environment can often use whatever probe you use. The environment can use it to screw up the system, because essentially a local order parameter is something that the system couples to, and you can use that to destroy it. I'll try to be a bit more concrete. So yeah, and then these topological states of matter are more, in some sense, more stable because of that. So okay, for the rest of the lecture, my plan was just to kind of first discuss an example that belongs to the first camp, and then the Toric code, which belongs to the second. And the reason I don't want to jump straight into Toric code is I feel to build up some appreciation for what makes the Toric code interesting, it's good to have something to compare to. And the interesting thing is there'll be certain parts that look very similar in both phases of matter, but in other parts, you'll see clear differences. Yeah, so is there any questions at this point? Okay. So let me start on a fresh page. So first I'll try not to go too much detail, but I want to give you a bit of a sense of, in this quantum context, how do you think of symmetry breaking? And the best example to discuss is the quantum Ising model, and it'll also, many of the things we discuss will kind of set us up for discussion of the Toric code as well. So it'll be good time investment. So let's look at a quantum Ising model as an example of spontaneous symmetry breaking. So as usual, as I emphasized, we have to first specify our Hilbert space, where we're living. And this model you can define in any dimension, but I'll be looking at a 1D system. In particular, I should say one spatial dimension. You might also call it 1 plus 1D if we count time as an extra dimension. Right? So one spatial dimension on a lattice here, and each side will again be a spin and a half, with X, Y, Z being the Pauli matrices, as I introduced earlier. And then one of the simplest Hamiltonians you could potentially write down, something like this. So we're in 1D. So let me first write the Ising interaction, just Pauli Z on qubit n, coupled to Pauli Z in qubit n plus 1. And then a single side, you can call it magnetic field, transverse field. Okay, so this will be our Hamiltonian with two free parameters. And so let's see, what can we say about this Hamiltonian? And it's often the case, like similar as in field theory, when you're given a system like a Lagrangian Hamiltonian, it's useful to first look at the symmetries it has. And then the symmetries will be very important for understanding the two different behaviors that can happen. And note, it has a symmetry given by doing a Pauli X on every side. Or in other words, it flips every spin, right? If you started with up, this will map it to down. And you can note, okay, clearly Pauli X commutes with Pauli X, so that's a symmetry. And it anti-commutes with a single Pauli Z, but since you have two Pauli Z's, minus 1 squared, so indeed you can check that this is symmetry of the Hamiltonian. And we also call it a Z2 symmetry, like it's in the group of two elements, because indeed this follows from the fact that if I square Pauli matrix, I get identity. So doing the symmetry twice gives you the identity. Right? Okay, so an order 2 symmetry. Okay, so let's try to get to know this Hamiltonian. So naturally, it'll help to look at two different limits, right? So case 1, let's say J is 0, no interaction, so to speak. And then let's say G is positive. Then the ground state likes to minimize the second term. So it likes to minimize this Pauli X term. So then the ground state is basically, let me just first write it. So what I mean by plus state is a superposition of an up and a down spin. So you can kind of see it, because if you were to start in the up pointing direction, and if you apply Pauli X, it would end up pointing down. So the Hamiltonian likes to fluctuate up and down. So definitely doesn't want to be in either of those configurations. And you can check that this superposition is naturally an eigenstate of the Pauli X, right? Because this gets mapped to this and this gets mapped to this. And here the tensor product n just means, it's completely decoupled. Every site is in this plus state, and they're kind of unentangled with each other, right? So we just write it out as plus, plus, plus. It's a simple enough ground state. And note, it is symmetric. Right, if I apply products, or product of Pauli X, it leaves a state invariant. Okay, maybe it seems natural that a symmetry of Hamiltonian is also present in the ground state. So we'll see a counterexample in a moment. And then we're talking about gap phase of matter. So let's check the energy gap above this state. So again, in this limit, right, we can just focus entirely on this thing, on this part of the Hamiltonian. The other part is 0. So it's easy enough to see. The first excited state will be when I violate one of these spins. So let me just sketch it out in this energy way. So far we got the ground state, right? So the ground state energy is basically minus G for every site. So minus G times L. L is the size of the system. And then here the ground state was just this. And then the first excited state, right, you can already see is when it's almost everywhere the ground state except one spin is flipped. And so then where minus is, as you might imagine, it's this, which has the property that x minus is minus the original state. So a lot of minus here. It's kind of the minimal way of violating the ground state condition. And we can directly kind of infer what is the energy, right? So it's the ground state energy, but then you can check it's 2 times G. Kind of, you go from minus G to plus G. So, and then of course you have other levels as well. And note there's actually many of these, there's actually times L, right? Because you could put that minus sign on any location. So at this point you actually have very many, but we don't care that much about that. The point is this energy gap delta is 2G, which is non-zero, and it's independent of system size. So the system, so we have the system is symmetric and the system is gapped. Okay, so it's already a gapped phase of matter, and in some sense it defines the trivial one. This is our reference point. Anything that looks like this shouldn't be called interesting, right? It's as featureless as it could be. Okay, so the ground state of this guy is pretty boring. So let's look at the other limit, phase 2. So we're gonna now put G to 0 and say J is positive. So at this point, all that matters is this what's called the Ising interaction. And like, what does this like to do? Well, it likes basically the ZZ interaction likes all spins to be aligned in the same direction, actually. So we can see how much I want to say here. The ground state could be something like this. You know, where now all spins are pointing up. Like, let me just write it down. So it's up, up, up. You can see that, you know, Pauli Z is +1 on this guy and +1 on this guy. So the product is +1. And note, if J is positive, we want to minimize Z. We want to minimize this thing, which means maximize Z times Z. So you can check. Yeah, this is the ground state. Or there's another option. They can all point down as well. Right. So to note, for this state, this has Zn minus for every site. That also means Zn plus 1 on 2 guys is plus. So that's why it doesn't matter if it's up or down. So we see there's a twofold degeneracy. The ground state is not unique. In fact, you can take any superposition of these two states. Okay, so it's a two-dimensional Hilbert space in the ground state manifold. So the energy looks as follows, right? So again, let's schematically plot the energy. So we again have a ground state, but now there's two. Let me just, they're actually on top of each other, but you know, just to emphasize, there's two. And it's all up and all down. So the degeneracy, and the ground state energy is minus JL, let's say on a periodic ring. And now again, we can ask about the excited states. For example, one option, right, is very similar to the above discussion where almost all of them are in a ground state, except one spin is flipped. Right, that's an excited state. This is energy ground state, but then actually it's plus 4J. This has to do with the fact that this interaction has ZZ is -1, but also this interaction has ZZ -1. And so for each of those, you go from the ground state value 1 to -1. So it's 2 times 2J. So it's 4J. So that's an excited state. But actually, it's not the lowest energy state. There's a state in between, which is where you only, like clearly it would cost less energy to only have one so-called domain wall, right? Where an up spin meets a down spin, because that's where you pay energy. So you could have something like this. It keeps going, where you only have one location where they're not aligned. It's like a kind of domain wall between the two different types of ground state order. And then you can check that this indeed, well, let me just write it like this. The gap is actually 2J. Note it's actually kind of it's kind of interesting. It depends a bit on boundary conditions, because if you imagine a system on a periodic ring, this scenario I drew is actually impossible, right? Because if you flip once, by the time you get around the system, you're gonna re-encounter the upspins. So you're always forced to be up here. And actually, for a deep reason I'll discuss in a moment, and actually be very similar to what we discussed in the Toric code in a moment. But if you ignore boundary conditions for a moment, you just have an infinite system, you just don't care what happens very far away, you can create this excitation of a single domain. But either way, whichever one you want to consider to be your first excited state, right? Either this level, the point is the system is gapped, right? So we're gapped. But note, we are not symmetric. There exist states that are not symmetric. For example, all up, if I apply the Pauli X symmetry, it will flip each spin and it give us the all down configuration. Right? So as a symmetry should, it doesn't change the energy, but the system doesn't need to be invariant under the symmetry if you have spontaneous symmetry breaking. So this is why we call it spontaneous symmetry breaking. The Hamiltonian is a symmetry that's not respected by the individual ground states. And this can be detected by a simple order parameter, which is if you have the ground state, it doesn't matter which one. If you calculate this guy, for any two locations along the chain, right? So can have very far away sites and an M, arbitrary distance. You can easily check at the ground state, expectation value of this is +1. And if clustering holds, so if you have two very far away observables, if the ground state doesn't have long range entanglement, you expect the correlation function to factorize. But of course, a product of two numbers can only be non-zero if the individual things are non-zero. But that's exactly an order parameter. This is probably Z detects whether you're pointing up or down. So it's kind of an order parameter. But even just the 2-point, you can show that having this long-range order and the so-called 2-point function is enough to tell you that you're, together with locality, it tells you that you're in a spontaneous symmetry breaking phase of matter. So this is a local order parameter. And note, you can definitely show that in the simple product state, if you calculate, this was the other regime where we started in, if you calculate the same 2-point function, it's 0. One can easily calculate that. So that order parameter really seems to distinguish them. And in fact, it turns out one can exactly solve this model, which I won't do in the interest of time. So one can solve, at least in 1D, and solve the 1D quantum Ising model. And I saw you had a few references on your webpage. For example, one of the books mentioned there is like by Fredkin. I think section 5 of Fredkin discusses how you can solve it exactly. So if you're interested, see section 5 of Fredkin's book. He essentially maps it to some free fermion problem and solves it. I just want to give you the physical result, what happens if you solve it. Because the point is, so far we just studied two limits, right? Only this term is present or only this term is present. But the kind of thing that makes phase of matter interesting is hopefully that they're stable, right? If we're talking about some infinitely fine-tuned thing, that would be less interesting. So then with that exact solution, one can, for example, see how does the gap change, for example, as a function of tuning parameter. In fact, let me just, normalize things. So a gap in units of J. And again, J was the, to go back up, so the Hamiltonian. Right? So J was the thing in front of the Ising interaction. So what I'm going to do is I'm going to tune from the limit where this is dominant to the limit where this is dominant. Okay, and see what happens. So for example, in G is 0, we're in this Ising ordered phase. And basically, you can, oops, let me do it in red. Oh, in red. You can show from the exact solution that there's a gap closing when this ratio is 1. In particular, the gap function is just, sorry. From the exact solution you get, it's just essentially this. And I'm just specifying to the case where non-negative. So here we see a gap closing. So that's already in line with our arguments that these two different regimes cannot be connected by a path of gapped Hamiltonians, even though individually they're gapped. So particularly this whole regime we call spontaneous symmetry breaking, and this whole regime, well, people tend to call it just trivial to denote it's not something else. Good. And you might wonder, okay, if it's supposed to be spontaneous symmetry breaking, that means there's 2-point functions should detect this whole phase. And indeed, from exact solution, you can plot, let me do it like this, the limit of this 2-point function for long distances as a function of the tuning parameter again. And then the curve looks, so far we calculated exactly here that it's 1 when this parameter is 0. And then it doesn't immediately drop to 0, it goes like this. And then it's 0 beyond the critical point. So you see in the symmetric phase is identically 0. There's no symmetry breaking. It's everywhere non-zero here. And again, note we have some interesting behavior here. Turns out to have an interesting critical exponent of 1/4. It's a so-called critical exponent of the Ising CFT. This is an example of a very simple looking lattice model with no Lorentz symmetry, whatever. But if you tune it to a critical point, you have the emergence of a whole conformal field theory, not even just Lorentz symmetry, and a bunch of critical exponents. And that's, for example, also discussed in Franklin's book and the other many of the other references mentioned there. Right. And then, so these are the different phases of matter, gap phases of matter. And as I already hinted at, in addition to having certain ground state properties, they're very interesting. Well, okay, very interesting. They have some notable properties about the excitations, as we discussed here. So we already saw this curious property that some excitations in the ordered phase, in the symmetry breaking phase, are not created locally. And actually, the reason I want to emphasize it a bit is it actually sets up the stage also for the 2D case. And maybe it's related to what Steve Simon discussed, because it also happens in these fraction quantum Hall states. So again, to orient ourselves, let's first look at the trivial phase. When trivial term is much larger, right? So when the ground state was roughly just a bunch of losses, and then we saw that the first excited state was something like just a single spin was flipped, right? That's what you saw above. So it's kind of maybe the natural scenario. You locally perturb the system, you pick it out as ground state, and that's like this is you can call it the quasi-particle of the system. This can run around and will behave as a kind of effective degree of freedom in your system. Oh, I see there's a question. Let me check. There's a question, so let me read it out loud. Classically, when we consider spontaneous symmetry breaking, we see that symmetry breaks as we move from one phase to another. For example, to the Ising model. However, in the quantum case, spontaneous symmetry breaking occurs at different energy levels. So the ground state and first excited state in different phases. Right. So okay, it's a good question. I would say spontaneous symmetry breaking is a property of the ground state. So yeah, it's really defined as a property of the ground state, but it also informs a property of the excitations. And it is also there in the low energy excited states. For example, as these pictures I was drawing here, you can still see any of these states, right? If I flip all the spins, I don't get the same state. So even the excited states are not symmetric. But somehow it's really inherited by the ground state, right? If I have like a massive quantum state, and that's not symmetric, and if I perturb it locally a little bit, right? That total state is still not going to be symmetric. So it is inherited by all the excited states, even though we only need to define it for the ground state. But right, so let me see the question again to see if I so and then in the quantum case, when the symmetry breaking occurs at different energy levels. So yeah, maybe not fully understanding it. So let me just say a few things. So so here again, I wanted to say we're always looking at ground states here, just for different choices of parameters. So it's when this parameter is very large, the ground state is symmetry preserving. When this parameter is very large, the ground state is symmetry breaking. So I'm always making a statement about the ground state, and then you can interpolate between the ground states. So I'm not trying to interpolate from low energy to high energy. I'm trying to interpolate from the ground state of one set of parameters to ground state of the other set of parameters. So in that sense, it's a ground state property. And it is a good question whether excited states are in different phases. And maybe a cop-out is if we're defining phases in terms of ground states of kept Hamiltonians, you'd first have to construct a different Hamiltonian of which your excited state is a ground state. And if that's not possible, then it's not as easy to make a statement about it. That's maybe the kind of mathematical answer. But physically, I would say we're defining phase matter as a low energy property of the ground state. And then we ask what are the consequences of the excited states. I think that is the clearest way to organize thinking. And that is kind of what I'm trying to discuss now. But okay, I hope that helps, but let me know if I misunderstood the question or if there's follow-up questions. So yeah, feel free to chime in at any point. Okay, cool. So yeah, and that sets up nicely for what I was going to say next. So if J is much bigger, then we're in this spontaneous symmetry breaking phase where we saw that local, how should I say it? Local perturbations create pairs of quasi-particles. Let me use Q.P as an abbreviation of quasi-particle. And as I mentioned, if you're not familiar with the notion of quasi-particle, as the name suggests, it looks like a particle, right? Like a fundamental particle, like a quark, whatever. But the point is, it's not literally a fundamental particle. It's just kind of a repackaged thing. And in this particular case, let me just try to make it clear. So in the ground state, right, one of the ground states we can start in, and I see a notification in the chat box, so I'll get to the question in a moment. So the ground state might be all up, right? But then imagine we do a local perturbation, right? So someone kicks my system, right? And a local perturbation is gonna have a local effect, right? So for example, maybe one spin has been flipped, right? Now, unlike this trivial phase, this is not a single quasi-particle. It turns out it fractionizes in two effective quasi-particles. The reason for that is that we pay energy here and we pay energy here, right? Because it's a ZZ interaction. So we say, so basically the point is the system can time evolve and you can, for example, continue flipping spins without extra energy cost. For example, note that this state has the same energy cost as the state above because I only pay, you only pay for the main walls. And it's the domain wall excitations that can move freely. So the fundamental quasi-particle is one domain wall. Like if you, to emphasize this, if you flip a single spin and you literally time evolve for the Hamiltonian, you'll see that these two domain walls separate out. There's nothing gluing them together. They're deconfined, is what some people call it. But so the kind of very interesting scenario where the fundamental quasi-particle is single domain wall, but you cannot create a single quasi-particle locally, right? It's kind of clear if you start with a single ground state configuration, I cannot locally flip, like an infinite region of spins, right? Which is what you would require to get a single domain wall. And this is called fractionization. And in particular, I just want to say, okay, actually, let me first get to the question. Oh, there's two questions now. Let's see. Okay, someone said clear. Okay, Kartikeya said, okay, that clears it up. Great. And then, okay, new question. Something that confuses me is why all upspins or all downspins are true ground states. I could in principle choose a state within this two-dimensional subspace that respects Z2 symmetry and where expectation value or parameter 0. Ah, great. Yeah, great question. So you're right. The question is, I said, these are two valid ground states, and those don't respect the symmetry. But what if instead I choose a superposition? All up plus all down. So so-called cat state. It's like a macroscopic superposition of two states. That's a ground state as well. And that is symmetric. So indeed, but the symmetry breaking is not about there not existing a symmetric state, because you can prove any Hamiltonian always admits a symmetric state. You can always symmetrize. The point is whether there exist non-symmetric states. But that's why I was emphasizing here in this box here, the key thing that matters is not whether a single order parameter is non-zero, but whether you have long-range order and a two-point function. And the only note why I'm emphasizing this here, remember I mentioned it's only if something called clustering holds, that if the two-point function holds and you don't have long-range correlations, then you can use clustering. But note, like the example given by Rolando, which is this one here, violates clustering. It satisfies this property still. You can check Zn, Zm has long-range order, but it also has long-range correlation, so it doesn't allow you to factorize it. And you see a single expectation value of Z is still 0. So that's why I emphasize that this is the better probe to look at, because this is independent of the choice of ground state. And physically, it still contains the picture of spontaneous symmetry breaking. It tells you have long-range order in an observable that carries charge under symmetry. Because even at face value, even though this is symmetric, it's a very weird state, right? It's a bit like Schrödinger's cat dot experiment. You have an all up and all down state. It's like a macroscopic superposition, and it's not a physical state you'd expect. And you can argue that it's actually not a robust state. If you initialize in this state and you have only epsilon decoherence to the environment, you'll collapse into one of these two. But the main point perhaps is that all the interesting properties, like the one actually I'm talking about now with the fractionalization, like the fractionalization of quasi-particles, follows from this two-point function. And so if you're interested in those kind of physical properties, you don't have to worry about which ground state you choose. Yeah, that's a great question. Let's see this one. Okay, cool. I cleared it up. And okay, so I was emphasizing the point of fractionalization, and I want to maybe put a point, like see, Steve Simon's talk. If he talked about fraction quantum Hall effect, he must have talked about the fact that a single electron could sometimes fractionalize. Like in standard model, we think of an electron as a fundamental particle, right? It doesn't have any substructure. But if you put an electron in these fraction quantum Hall states, and you see how it behaves, it turns out it fractionalizes into kind of 3 fractionalized particles, each with charge either, the way it's fractionalized depends on the phase of matter in. There are different types of fraction quantum Hall states. But the main point is a single electron fractionalizes into 3 smaller pieces. And you cannot create those pieces by themselves, right? There's no object, ignoring quarks, where you can insert a fractional charge into your system, but you can create them locally, and then it can fractionalize. And that's very similar to the picture we saw here on the right. You can't create a single domain model, you can create them in pairs, and then they can delocalize. Okay, and so good. And in terms of phase of matter, you can indeed show that these 2 different Hamiltonians, to link it back to this early definition, right? So if I phrase it as I'm given 2 Hamiltonians, this Ising interaction and the single side term, you can indeed show that they cannot be connected. By some, gapped Hamiltonian H lambda, which interpolates between these 2, right? So particular H0 here and H1 here. You cannot have a gapped Hamiltonian since, but it's kind of true for obvious reason, since the ground state degeneracy is not equal, right? We saw here, the degeneracy is, has a unique ground state degeneracy is 1, you might say. and here the degeneracy is 2. So if you have two Hamiltonians with different sizes of degeneracy, it's clear that you cannot smoothly deform one state into 2 or vice versa. At some point, 1 has to go to 2, the gap has to come down in order for the system to restructure the amount of ground states. So that's exactly what happens here. You can also track here the degeneracy is 2 throughout, and here the degeneracy is 1. So you cannot smoothly connect them. But in some sense, that discussion is a bit too quick, because you might be worried that the degeneracy is unstable, right? If you're given a system with twofold degenerate ground state, it might be less interesting if you can add an infinitesimal perturbation, no matter how small, and kind of split the degeneracy and get a unique ground state. And this has to do with stability. What about the stability of these degeneracies? And so the ground state degeneracy of this Ising Hamiltonian this twofold ground state degeneracy is stable to all Z2 symmetric perturbations. And in the above, we saw an example, right? So if I start with this Hamiltonian and I add, a little bit of a epsilon x, that's the Hamiltonian I was studying before. And I was claiming already that the twofold ground state degeneracy is stable. You can show that. And when I say stable, it means, if you make any perturbation large enough, you can drive a transition to a new phase. But the question is, will it immediately get destroyed or not? And it turns out that this choice of Hamiltonian was not special. You can do any, you can do epsilon, yn plus 1, or anything that's symmetric with respect to the Ising spin flip symmetry. You can show that's all stable. So that's already good. Okay, so that means it's not infinitely fine-tuned, but the ground state degeneracy is unstable to non-symmetric perturbations. In particular, suppose we have, again, the Ising Hamiltonian, but now I perturb with a tiny bit of a single side field, right? Note that this kills the product X symmetry, right? The symmetry was this. This is now killed because a single Z does not commute. But you can add it, right? It's a physical thing to do, breaking the symmetry. And then you can easily check that the ground state is now immediately unique. In particular, now you want to be all up. Let's say epsilon is non-zero, positive. The ground state is now all up. And the first excited state is a single spin flip with energy 2 epsilon. So okay, so we discussed that spontaneous symmetry breaking has a phase of matter and has some interesting properties. In particular, it means that quasi-particles in 1D are fractionalized and is distinct from this other phase of matter, quantum critical point, etc. But all of that hinges on you not breaking the symmetry by hand, which kind of makes sense, right? Like if you have spontaneous symmetry breaking and then you break the symmetry by hand, you kind of lose what makes phase special. That's intuitive, but it is an instability nevertheless. And then you could ask as a segue, like, do we always suffer from such instability, right? Do there exists quantum phase of matter stable to all gapped phases? Sorry, to all gap perturbations. Just try it. Again, when I say stable to all perturbations, any perturbation you add, if you make the prefactor large enough, can drive a transition to another phase of matter. It's always the case. But again, is there a phase of matter where if you perturb with sufficiently small perturbations that it's stable no matter what choice you made of type of perturbation? And the above is a counterexample. Like this, so this is not an example because this particular perturbation kills it. And it turns out it has been proven in one spatial dimension, so maybe as 1 plus 1D, where 1D is time, The answer is actually no. The simple linear symmetry breaking is as interesting as you can get in some sense. Okay, there's some caveats. This actually, again, has not been proven that long ago. It's 10 years ago-ish. So it's this archive paper by Norbert Schuch and company. I hope, I can't read my own handwriting. It either says 3 or an 8. So, and it's a kind of interesting classification, phase of matter in 1D, using tensor network states. And it was proven that, yeah, basically just symmetry breaking. And some other things that are, again, not stable to all perturbations. But if you go to 2 spatial dimensions, the answer is yes. That's what I'll discuss in the remainder of this lecture. I realized I spent quite some time on the Ising model, but actually I think it's quite useful background because it'll also set up many of the things we'll discuss for the Toric code example. Maybe we can take like a 5-minute break or something, so people can recollect a bit, and then for the remainder, 20-ish minutes, I can give you a bit of a sense of the Toric code state.
Yeah, that sounds good. Yeah.
Okay, cool. Thank you. Then yeah, I'll be back in.
So we take 5 minutes and then come back. Also for the audience, take the time to think about questions.
Thanks. And just saw that there was another question about the previous part. Question is the analysis you've made at 0 temperature. Just summarize what would happen at finite temperature. They still have the phase transition. Do you still have entanglement? Yeah, it's a great question. So it turns out that it depends on dimensionality. It turns out in 1D, the case I was discussing, it actually goes away at finite temperature. There's no more finite temperature transition. But in 2 dimensions or 3 dimensions, indeed, there's a finite temperature stability as well. And then whether there's still when there's still quantumness, yeah, it's a bit hard to define. In some sense, there will always be some residual quantum fluctuations. But whether you actually, actually, I would say that's also kind of an active topic of research, people trying to define what precisely it means to have quantum entanglement at finite temperature. And there's just, at the moment, there seems to be different types of definitions. And people are kind of still exploring the landscape of when does something have an interesting or notable type of entanglement. So yeah, it's kind of a short answer saying that requires a longer discussion. Yeah, thanks for the question. Okay, so in the remaining 20 minutes, I want to give you this example of something that's stable to all perturbations. Okay, and this is the Toric code model, and the minimal example is in 2 spatial dimensions, and it's introduced by Kitaev in the late 90s, as shown here. And again, let me start by introducing the Hilbert space. Now we're looking at a square lattice, and the degrees of freedom will again be spin-halves, but now for convenience, we'll say they live on the links of the square lattice. And the Hamiltonian is defined as follows. For every vertex of the square lattice, we have the following 4-body product, Z, 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 Z. So there's product of 4 poly Z's. And then for every plaquette, we have a product of X's, poly X. Okay, so it's a 4-body interacting system. There are actually ways of experimentally motivating this model as well, or variations of this model. But for now, I'm just gonna, I just accept we can imagine 4-body interactions. And it helps also to introduce a name. This is often called the vertex term, A. Just vertex because it's associated with vertex of a square lattice. And this is also called a plaquette term, because obviously it's associated to plaquettes. Good. And this is the Toric code Hamiltonian. The name will become clear in a moment. So, okay, so far we've defined a Hilbert space Hamiltonian. Now we understand what is the low energy structure, what's the ground state. And to solve this Hamiltonian, because it turns out to be exactly solvable, first observe the following nice properties. Each of these, they're called stabilizers sometimes. because they stabilize the ground state. Each of these stabilizers, they square to identity. And again, that follows from just the fact that a single Pauli matrix squares to identity. Okay. So that's all really useful. So what that means is that the spectrum of each of these terms is just 1 or -1. Okay, so that already gives us a sense that the spectrum of the Hamiltonian will be a bunch of, pluses, okay, some integer value spectrum. And then also you can check that these vertex and plaquette terms, they commute. For example, simple example, let's say we have the z term on this part, and on the neighboring plaquette, we can look at the x term. And of course, there's a single z and x, they anti-commute. But note that they always come in pairs. So we get -1 squared. So indeed, they commute. Excuse me. So those algebraic properties tell us first a variety of nice things. First of all, the ground state has all of these terms equal +1. That's the lowest energy state, right? You have minus this term and minus this term. The lowest energy state is when all terms, all A and B terms are +1. And the above discussion tells us one is the maximum eigenvalue, and since they all commute, they can be all simultaneously 1. For all vertices V, plaquettes P. Okay. And note, we also get that the excited states will correspond to flipping one of these values. For example, we'll have, you get different choices, but for example, one of the star terms might be -1 instead of +1. The main point is, from this you can argue that the gap will be at least 2. Okay, so the system will be gapped. But what is not clear is what is the ground state degeneracy? Right? Does it have a unique ground state or not? And just to tell you, it turns out the ground state is Hamiltonian will neither be in a trivial phase or neither will it have spontaneous symmetry breaking. It realizes a completely different type of phase of matter. Okay, but some of the things we discussed in the symmetry breaking case will kind of help guide our thinking. Okay, so let's see what's the ground state degeneracy. To get a better insight into degeneracy and more general, better insight into what is this phase of matter, it helps to have a geometric representation of the ground state. So it turns out, okay, so can we just say to explore the ground states, it's helpful to interpret this vertex condition. Now, in the ground state, each vertex term is +1. We want to interpret it geometrically as a loop condition. It's actually quite intuitive once you think about it. So again, let me go back to the lattice. And we have spins, right? They might point up, or they might point down. Like this. And I'm just giving an example of a legitimate state. And note, the way I'm choosing this is, note, each vertex has AB +1, right? For example, this vertex term is just the product of Pauli z's. So here you get +1 times +1 times -1 times -1. It's indeed the product of these z's is +1. You can just check this classical configuration indeed satisfies this being +1. This is one of many possible things I could have drawn. So what's the point? Well, you can very efficiently interpret this geometrically as a loop. Let's say whenever we have, say, a spin pointing up, I'm just going to represent it as an empty bound. Whereas whenever the spin is pointing down, I'm going to color the bound. Okay, so now note, for example, here, going down. So in other words, I can visually represent the state. as this loop. Sorry, I'm just gonna look at lattice. So all the information is essentially contained in this. And then, yeah, it's a one-to-one correspondence, right? Whenever I draw this picture, you can draw the spins. And then, and okay, this lattice goes on. So then you can interpret the AVs plus, the AV being +1 as a closed loop condition. The loops are not allowed to end. Okay, so, and moreover, we can interpret the plaquette term as a resonance. For example, let's take this plaquette. If I apply BP, I mean, let me also do it on this. Yeah, let me just do it here in the interest of time. If I, what does BP do, right? Plaquette term flips all the spins around the plaquette. But if I flip all the spins, that means, it will flip an empty bond to a colored bond and vice versa. So you can kind of see that after doing this, I will get this configuration. Right? So again, this is plaquette P, where I acted. So it resonates. So BP +1, what it corresponds to is resonates loops. It makes sure that you have superpositions of many different loop configurations. So in summary, with this little useful picture, we get that the ground state of a Toric code is somehow a superposition of closed loops, right? So, for example, one ground state is something like this loop, and then you have another one. You can even forget about the lattice loop, something like this, and what I call resonances, I just mean all kind of these recombination moves that I was showing here. Okay, so in other words, we sum over all loop configurations, and the ground state is superposition problem. And that's indeed right. So again, the closed loop tells you the star term is happy, and this effective superposition tells you the plaquette term is happy. So that gives you an interesting kind of picture of the Toric code ground state. And it also tells you how to count degeneracy, right? So for degeneracy, let's consider system on periodic boundary conditions. Periodic boundary conditions. What that means is our system lives on a torus, right? If I take a square patch, right, and identify top and bottom and left and right, what that means, you're creating a torus, right? And note you have different sectors. We have 4 distinct sectors that cannot be coupled to each other, right? To explain what I mean, we have 4-fold ground state degeneracy. To see that, let's first consider, we can start with the empty loop configuration. And then we can add all local resonances, right? So on each plaquette, we're gonna flip the loop. So for example, we might have a little loop appearing, right? And all of the other ones. And that forms like a whole macroscopic superposition of states, and that's one ground state. Okay. Let me, instead of say 1, let's say, psi1. But another ground state is where I start with an empty, no loops, but I only have one that kind of wraps around a handle of the torus, like a non-trivial loop around, right? And then do all local resonances. Note that these are distinct wave functions, right? If I start with a non-trivial loop around the torus, by only doing local resonance, by locally recombining loops, creating or destroying loops, I can never create a non-trivial winding around the torus. It's not even clear on side, it's maybe worth adjusting on a bit, but you can convince yourself locally, you cannot go from top to bottom. So in fact, these are different states. Okay. And similarly, now you can imagine the other two. It's about starting say, if you have a loop, maybe in this direction, and then plus resonances. Again, it's a different state. And then finally, the fourth one is if you start with a loop both on this and in this direction. And again, it's different. So the point is, these are all four ground states, right? They're all closed loops, and you resonate all possible local moves. So that's ground state energy, but they're also distinct. So you have fourfold degeneracy. And note, this actually grows with the genus of the manifold, actually. So you can have more complicated manifolds, and the more holes you have in your manifold, the more ground state degeneracy. But the interesting thing is, these ground states cannot be locally distinguished, right? If I give you any of these wave functions, by just taking snapshots by looking at local measurements, you won't be able to tell which one you're in, right? Because the minimal thing to measure is whether there's a loop. Like the number of loops that wind around is odd, right? That's very hard to measure. That's also kind of why these states are called topological, because at different ground states, you can't tell which one you're in. You can just tell that they should exist and they're distinct, but you cannot measure which one you're in, at least not locally. But it also means you can use that to prove that this ground state degeneracy is stable to all perturbations. Sorry, in the interest of time, I sadly don't have much time to give arguments or proofs, but I hope the intuition is clear, actually, right? Because if you cannot tell which ground state you're in, the environment, the perturbation cannot tell, because the Hamiltonian is local, right? And energy can only distinguish, you can only measure local things. And if you cannot locally measure which one you're in, the Hamiltonian is not able, no matter what the perturbation is, to locally tell, to choose one of the four ground states and make that a unique ground state, right? So I hope that's kind of intuitively clear. So indeed, so the top statement implies the bottom statement. Notice it's dramatically different, to contrast, this Ising chain example, right? Where you can definitely tell the local ground states apart, right? For example, sorry, all the way back up here. It's easy to distinguish the all up from the all down, right? A poly Z does exactly that. And that's why adding a poly Z, right, was able to destroy it, because it can distinguish the two ground states and make one unique, right? So I hope that clarifies that in the toric code state, if you believe me that you cannot distinguish them, it implies the stability to all local perturbations. This has to do with the fact that you can relate this to field theory. Maybe this was discussed by Steve Simon's lecture or will be discussed by Outland, but it has to do with the fact that this is related to the low energy theory. Is a topological field theory. So remember in the beginning I was saying that because the system is gapped, it seems like a very innocent field theory, but it turns out there's some topological degrees of freedom left over, and those need to be specified at the field theory level, and you can write down a field theory. And those kind of universal descriptions also allow you to derive that there should be degeneracy. I mean, this is like a lattice-based perspective. And the remaining few minutes that I have, I just want to tell you about the excitations. And this is why I emphasized so much earlier on this fractionalized nature of the domain walls and the 1D Ising chain. Because here we'll see a similar thing, but again, it's much more stable, because now there's a phase of matter stable to all perturbations, right? And just to, so let's talk about the excitations in just a few minutes. So we already discussed the ground state, right? And this is fourfold degenerate. And now the gap will be 2, where in the excited state, AV plus 1 will no longer hold for some vertex, or BP plus 1 will no longer hold, right? That's where we pay energy cost. So let's get some intuition for what it looks like. An excited state might look like something like this. Again, this loop picture will be very helpful. For example, this could be a closed loop that carries on. But what if you have one loop that just ends, right? Okay, So at this vertex, AV is now no longer +1, it's -1. Okay. We see we get a single violation. And again, you can have resonances. Oops, you can have resonances such that globally, all the plaquette terms are still happy. But you have this one vertex where this star term is not happy because you have an open string, right? Which means you have a single downspin on that vertex. And that's an excitation. Naively has energy cost 2. But you can also see it cannot be created locally. It's very similar to this domain wall picture we had, right? If you start with loops, with this kind of superposition of loops, you can't really create a string that ends because at some point it's going to end somewhere else, right? If you keep tracking it, it's going to end in a second guy. So the point is, these excitations, which are also sometimes called E-anyons, and again, if you've seen anyons in Steve Simon's talk, this is an example of an enyon, just a name, E-enyon. These particles, enons, can only be created in pairs. So this is an example fractionization. Again, that's why I emphasize so much the 1D case. If that point came across in 1D, it's very similar to this, right? You can have these delocalized string endpoints that can move separately, but you cannot create them individually. And then maybe the last thing I just want to mention, similarly, if you violate the plaquette condition on one plaquette, this is called an M-enyon. And again, you could only create this in pairs. And then the last thing I want to mention, because I'm out of time, the last thing I want to mention, again, linking to Steve Simon's talk, he probably discussed that if you have anyons, what makes them interesting is that they have non-trivial braiding relations. And you can show that if you take these particles, you start with an E-enyon, you start with an M-enyon, so that means one violated the vertex term, one violated the plaquette term. If in a function of time, you kind of exchange them, you can show the wave function picks up a -1 phase factor. And this can be proven by noting a very simple fact that E-anyons, the way they're created by acting with a product of poly X all along a line, right? If I have a lattice, and if I act with X on a bunch of guys, then you'll see that this star term and this star term will be violated once you act to this. This has to do with the fact that the star term anti-commute to the poly X. And similarly, M-anyons are created by product of poly Z. And then you just use the fact that X and Z anti-commute. So this is just an aside if you're wondering how to prove it. But this is the main upshot here. So just to summarize, so in 2D, you can have these phases of matter, which have ground state degeneracies that are stable to all possible perturbations, unlike in 1D, for the reasons that I mentioned, because you can't detect it. And these kind of same very interesting ground states give rise to quasi-particle excitations that cannot be created locally. And so they're kind of more non-local in nature, similar to domain walls, but more stable. And if you braid these particles, they can have exchange statistics that goes beyond fermions and bosons. In particular, neither bosons or fermions have these exchange relations. And in fact, this kind of exchange statistics are called semionic statistics. It's something that doesn't happen in standard models. You can only get it in these kind of emergent systems. So a bit for the rush towards the end, but I hope some of the key messages got across. I hope it gave you a bit of a taste of a kind of quantum phase of matter that one can explore. And yeah, thanks for your time and attention. I'm happy to stick around more for those questions, but I just wanted to end here.
Oh, very nice. Thank you for very nice and comprehensive talk on this topological basis of matter. So yeah, I think we have some some time for some questions. Oh, I think there is a question in the chat already.
Okay, let's see. Okay, so the question, let me read it out loud. I think there's a way to understand the ground state degeneracy of Toric code as a consequence of symmetry breaking of a one-form symmetry instead of zero form. Could you say some words about this? Like, what is the order parameter in that case? What's the symmetry that's broken? Yeah, that's an excellent question. So indeed, it turns out, funnily enough, that you can indeed understand the ground state of Toric code as an example of spontaneous symmetry breaking of an exotic type of symmetry. So Rolando is referring to one-form symmetries. So indeed, I can say a few words about that. Note that the ground state has something called a one-form symmetry. So what is a one-form symmetry? A usual symmetry, so-called zero form, is something that X on every side. So we saw this in the Ising model example. I flip every spin, right? A one-form symmetry, roughly speaking, right, in the interest of time, is something that X only on certain sides. Okay, so particular, if I act with Pauli X on sites along some loop, it leaves the ground state invariant. So what do I mean? If I have the lattice, right? If I say a loop, okay, now it's not the loop of the ground state configurations. So make sure I get it. Yeah. So if I act with X, like this is my loop gamma. If I act with X on every site, what it does, basically it inserts a loop on that bond, on those bonds. But as we discussed, the ground state is a superposition of loops, and hence it leaves the state invariant. And you can think of this as symmetry, right? For arbitrary choice of loops, the ground state invariant only doing a product X. So the point is the symmetry is supported on a loop instead of all of space. Right? Usual symmetries act on all sides in space. So that's a symmetry. That's a one-form symmetry, just a name. And in some sense, the claim is the ground state spontaneously breaks this higher form symmetry, one-form symmetry. And as Roland was asking, that means there should be a notion of order parameter, and that's correct. So maybe to draw the analogy, in the Ising phase, right, we saw product of Pauli X was a symmetry, and the order parameter was a single Z. Or in particular, we looked at a two-point function. So we need something that carries charge under a one-form symmetry. So the order parameter is a loop, or let me just write it down, is a product of Zj, where J lives on a loop on the kind of dual lattice. So what that means is, for example, let me actually draw, like, let's say a loop like this. Z, Z, Z. Right, it could eventually close back down to itself. Right? And note, just like in the Ising case, we had a global Ising symmetry and a single poly Z was an order parameter because it doesn't commute with the symmetry. Similarly, you can see, so this is the guy in red here. You can see that our symmetry, which acts with X, 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 you can see that this product Z anti-commutes with the symmetry, which is the product X. So in that sense, this red Z loop seems like a valid order parameter. And then the two-point function, now it's useful to think of the system maybe on a very long cylinder. Okay. The two-point function will be something like, just like we did in 1D, right? Like a ZI-ZJ correlation function. Now we can do a loop-loop correlation function. And if this correlation function where there's some distance r. And then if this is non-zero as r goes to infinity, we say, just like in the 1D case, we say it's spontaneous symmetry breaking for the one-form symmetry. That's very analogous to the 1D scenario. And then last part is the question asking, how does it tell you about the ground state degeneracy? Well, similar to the 1D case, certain ground states, again, in the 1D you have this scenario, you could choose ground states where clustering doesn't hold. For certain ground states, clustering should hold, which means you should be able to factorize. Okay, but that means if you have 2-point function, so it's a bit of a, okay, it's a good question. It's a bit of a, technical, how to say? Yeah, sorry, I hope I'm not alienating part of the audience, but yeah, so if we got that a 2-point function had long range order, you could argue that the single point function on certain ground states has to be non-zero. But if you find such a ground state, this means this particular ground state is not invariant under, doing the XXX guy, right? Because the point is these two anti-commute. And you can show, using that n-commutativity property, you can show what I wrote down. You can show that if you find a ground state that is non-zero expectation value for this, the symmetry breaking order parameter, you can show that the ground state is not invariant under the symmetry, but it tells you the ground state and product X on the ground state are distinct. Hence, you have a degeneracy. Because it's a symmetry, they must have the same energy. So you have a degenerate ground state. And we can link that back to the pictures I was drawing to go from this to this. Just act with product X on the horizontal, on the vertical loop. And that's how you insert or remove loops. And indeed, so that sense is actually very similar to the 1D scenario, where because you spontaneously broke the symmetry, you have multiple ground states which are related by the symmetry transformation. Okay, so I hope that gives some sense of in what sense you can think of topological order as this one-form symmetry breaking, and how it tells you the ground state degeneracy. Another question for Toric code: what if we consider symmetry under the modular group PSL27? Do we see spontaneous symmetry breaking? It's a good question. I have to admit I'm not that familiar with this way of thinking. I guess it's I can see how that should be a symmetry at low energy theory, right? Like kind of just reshaping your torus in some sense, right? Kind of like a spatial symmetry of the system. But as far as I understand, that spatial symmetry is not spontaneously broken in any way. It's really, you have to look at these higher form symmetries to think of Toric code as higher form symmetry breaking. But maybe I'm missing out something, but it's my understanding. Any other questions? Oh.
Yeah, it seems like there are not more questions.
Okay.
So yeah, thank you very much for the really nice talk. Yeah,
Thanks for the invitation. It was fun.